Our visible light occurs in different colors: red, green, blue, and colors in between. And each color is an electromagnetic wave of a slightly different wavelength. So a color is identified by the wavelength of the radiation that makes it up. Now, if I hold up a sheet of white paper here, it is not radiating white light, because paper does not radiate light in the slightest. Well, the reason that it is appearing to be white is because it reflects all colors back into your eye. So the white appears to be white because there is white light in the room, and this paper has the property that it reflects all wavelengths equally. When all wavelengths are present, then they blend together and they form what we call white light. For example, this smartboard behind us is a blend that reflects all of the wavelengths in the room, so therefore it appears to be white. Now, if I take this blue bottle cap, for example, it is not radiating blue light, but the reason that it appears to be blue, because out of the white light in the room, comprised of all wavelengths, it absorbs all of the wavelengths except the blue, which it reflects back to you. So it does appear to be blue. I can convince you that it's not radiating any light whatsoever. If I just turn off the room lights, then you can't see it at all, blue, black, or any other color. Now, this black cap has the property that it is not reflecting any light whatsoever. It is absorbing all of the wavelengths that strike upon it. Therefore, it is not appearing to have any color whatsoever. So black is not that black light is reflected. There's no such thing as black light. Black appears to be black because it's absorbing all of the light. And this is the one object that will have the same color in the dark. Now, if I heat an object up, then it will start to radiate energy out, because the atoms and the electrons in the object start to vibrate, and when electrical charges start to vibrate, they emit electromagnetic radiation. So heat comes off of the object because of the thermal motion of the atoms and electrons in the object itself, and this is radiated away as energy, as electromagnetic or as light energy. If you turn on your electric stove, then you can feel the heat coming out of it. If you put your hand near to it, and you might say, well, the stove is heating up the air and the air is heating my hand, but still, even in a perfect vacuum, you would feel heat because your stove is actually radiating electromagnetic waves of energy out. Our own body is also, in a completely dark room, we can detect other people because we can feel the electromagnetic radiation coming off of their bodies. The reason that we don't see it in our everyday life is because our bodies emit their electromagnetic radiation in the infrared part of the electromagnetic spectrum, which our eyes cannot see, but our infrared detectors can see them quite well. So we have the thesis that if we heat up an object, it's going to start to emit electromagnetic waves. Now, the object that we want to heat up and study is an object that does not contaminate the energy that it emits with any of the energy that it also reflects. So we want to heat up an object for study that will reflect no light at all. So we want to select a black body to heat up and to see what kind of wavelengths come off of it. So we will study this topic of black body radiation. Now, by black body, we simply mean that it treats all wavelengths equally. It will radiate one wavelength just as easily or readily with no preference as any other wavelength. It is indiscriminate as to what wavelengths it will radiate. We call it a black body because a black body is also indiscriminate as to what wavelength it will absorb. It will absorb all wavelengths. So if we heat up a black body to a very low temperature, it will emit radiation in the wavelength that we cannot see. If we heat it high in the infrared and micro, and if we heat it to a higher temperature, then it will start to emit radiation in the visible rate that we can see. And the longest wavelength, the lowest energetic electromagnetic radiation that our eye can see is the red. So the first temperature that we start to see in a heated object is of red wavelength. Then if we heated it up to higher temperatures, then it would acquire a shorter wavelength, more energy, higher frequency, and we would start to see yellow and blue coming off of this heated object. So if we do a graph that measured the intensity of the various colors or wavelengths that were emitted, then because it's a black body, it will emit all wavelengths. But depending on the temperature at which we heat it, it will have most of its emission at a certain wavelength. So that is that the curve that measures the amount of intensity at the different wavelengths is going to have very little up here in the ultraviolet. Then as we get into the visible colors, it's going to have most of its energy. And as we go back into the radio, it's going to continue to emit them, but it's also not going to emit as much. So most of its radiation is emitted at some temperature, which we call the maximum wavelength. Now, as we change the temperature to a higher temperature, then we are going to cause the peak of this radiation to move to the left. It's going to start to emit most of its intensity at a shorter wavelength. And the more that we heat it up, then the more that the maximum wavelength at which most of the energy is emitted will be into shorter and shorter wavelengths. So there is a relationship between the maximum wavelength, where most of the energy that is emitted, and the temperature at which we have heated the object to, such that the lambda max times the temperature is equal to a constant, which is 2.9 times 10 to the 6th, as long as we measure the temperature in Kelvin and the wavelength in nanometers. So this is how we can relate the color that we see, or the maximum temperature that is emitted from a black body, to the temperature that is on the body. Now that we can use this relationship to very easily measure the surface temperature of our sun. Our sun emits most of its energy in the yellow wavelength, as we can tell just by looking at it. So if we put in the wavelength for yellow light, then we find that the temperature, surface temperature of our sun is about 3,000 degrees Kelvin.